Hello guys, hope you had a nice break. We're gonna continue back with our YouTube lectures. And what I will do today is I'm going to go over springs quickly again, mainly compression springs. And then I'm going to cover extension springs and torsion springs. Just a brief recap, we said, if you have, some spring, basically if you zoom in on the wire, you're gonna see that this is how the wire is going to look like. And if you actually have a compression force applied on that spring, you are going to have a shear stress over here. And that shear is going to be equal to KB 8FD over pi d cube, where F is the force applied on the spring, D is your mean coil diameter, and small d is the diameter of the wire that the spring is made out of. KB is a factor used to take into account that helical or the change in curvature in the Z elevation, in the Z direction of that spring. KB is going to be equal to 4C plus 2 divided by 4C minus 3, where last time we said C is going to be, it's called the spring constant, and it is largely over small d. Okay, so it's pretty straightforward. If I ask you what is the maximum shear stress in a spring, in a compression spring as a result of this force and then this dimensions, G and then small d, you will just directly calculate this maximum shear, and you're going to tell me that the maximum shear is going to occur on the inner diameter of the coil. All right, how about the spring rate? We said the spring rate, and we got that from our the energy equation, and then all you have to do is just know that spring rate is going to be equal to d4 multiplied by g divided by 8 d cube over Na, where Na is the number of active coils. G is the modulus of elasticity, and then it's related to the modulus of elasticity, right? This is modulus of rigidity. It's related to E by the Poisson's ratio using this equation. This is really the rate, and the last thing is we know as a result of applying a force on the spring, you're going to have that shear stress, and there is a maximum value that shear stress could be on a spring, and we said this guy, the maximum shear in yield, right, which we call as SY, is going to be equal to 0.45 multiplied by the ultimate strength, and the ultimate strength of springs is going to be equal to A over D to the power M, where we look A and M from a lookup table, table 10.4 in my notes. So from table 10.4, for a given for a given wire diameter, you essentially get your A and then your exponent. And that is really it, guys, for compression springs. These are the main equations that you need to know. There's one more thing that I mentioned, which is the buckling of a spring. So what is buckling? Buckling essentially occurs sometimes, I'm pretty sure you might have heard of beam buckling, right? So if you have a beam, right, and then if you apply a huge force on that beam may actually do this, right, as a result of this load. And this is called buckling. And then I'm pretty sure those of you who have, kind of messed around with springs, if you have a very long spring, right, and then you try to deflect that spring a little bit, it will actually do this, right? And then if you do even more, maybe it's going to look like that. And basically, the spring is losing its function or mechanical function. When does buckling occur? Pretty easy in our case. We're going to specify a deflection. We're going to call that YCR, and this is the maximum deflection that a spring could have before it buckles. So if I deflect that spring up to this point, it won't buckle, but if I deflect it more than this from here, now it actually risks buckling. And this equation is provided in our notes, and I'm going to share my screen so you can quickly see it. Okay, this is our critical deflection, and the critical deflection is a function of the free length of the spring, C1 prime, C2 prime. These are all constants and are given to you. And lambda is, as I mentioned also last time, lambda is going to be equal to this. It's a slenderness ratio, essentially ratio of the length over diameter. Alpha is going to depend on the end conditions. So if the springs are, one end clamped and other end free, then alpha is 2, and then you're going to use a stick. Okay, so this is the buckling of springs, and then that is really it regarding springs or compression springs. Regarding the fatigue failure of compression springs, we said springs have two types. One type is pinned, okay, spring. We have pinned, right, or unpinned. By pinned, essentially we mean shot pinned. Shot pinned, I suggest you look it up on YouTube how shot pinned is done. Shot pinned, basically, you could have any piece of metal and then you shoot like tiny particles on it, and these particles will create compressive stresses on the structure. And as we know, if we have compressive stresses on the surface, then fatigue may not occur easily because you have you're closing the gaps, right, and then you are reducing the cracks, right? How do we do this? How do we evaluate the life or the safety factor for a spring in fatigue based on pinned or unpinned? If the spring is pinned, and these are all in the notes, it's going to have a maximum alternating stress that is equal to 35 KSI and the maximum mean stress of 55 KSI. Sorry, this is unpinned actually. This is for unpinned. And then SSM is equal to 55 KSI. And for shot pin, these are going to be greater than that. These are equal to 57.5 KSI here. And then if it's pinned, your maximum mean is going to be 77.5 KSI. All right, now to evaluate the safety factor for fatigue, we're going to use simply the modified Goodman. And we know the modified Goodman is usually sigma prime A over SE, right, plus sigma prime M over SM. Okay, so this is a basic modified Goodman criteria, and then in this case, sigma prime A and sigma prime M are what? Are the von Mises, right? In the case of springs, we don't have any, we have mainly shear, we don't have any axial stresses, so this equation is going to become like that. Tau A divided by SSE, and then this guy is your shear endurance, right? Shear endurance, not regular endurance. This is your shear endurance. It's like you have a piece of metal, and I'm trying to shear this. How many cycles could it last, or what is the stress that I should be loading the part so that it would last infinitely under torsion, right? This is your shear in endurance. Plus sigma tau M over SSM. Okay, so we're going to actually solve for this, right? Here's what happens. So in the case of, based on this criteria, I can basically solve for a safety factor, right? And if the safety factor we said is below 1, right, it means that the part is going to last some number of cycles, and then it's going to be. If the safety factor is actually equal to 1, right, it means that the part will actually last infinitely, for an infinite amount of cycles under this equation. So we can actually solve for this SSE using this equation. So here at the threshold, tau A will actually be equal to these guys, SSA, and tau M is going to be equal to SSM. From here, I can essentially solve for my endurance limit, and it's going to be equal to, based on this equation, for a safety factor of 1, it's going to be equal to SSA divided by 1 minus SSM divided by SSU. Sigma M divided by the way, guys, this is SSU, right? Okay, this is SSU, right? Sigma prime M will divide by the ultimate, right? So this is how we can solve for your endurance limit in shear, and sometimes you would see that they actually have a 2 over here if you are using Gerber, or it would be 1 if you are using the modified Goodman. In the book, when they are calculating the endurance limit based on these numbers, they are using the Gerber. Okay, and this is why we are using this, is we are essentially calculating the endurance limit based on the maximum alternating and the maximum mean. All right. So this would be your first step. And now that we have calculated our SSE, I could essentially come back and calculate my safety factor based on the modified Goodman. So based again on the modified Goodman, we know 1 over safety factor is going to be equal to tau A. Remember now I'm changing, I'm using essentially tau A, and I'm using this new value which I calculated, tau M divided by SSM. And now the safety factor is going to be equal to 1 over tau A divided SSU, guys. I'm very sorry about this. This is SSU always. SSE plus tau M divided by SSU. What is SSU? SSU is your maximum ultimate shear, or maximum ultimate shear strength of that music. All right, so really pretty basic, guys. If you have a spring and you are trying to calculate the safety factor for fatigue of a spring, the first thing that you have to do is identify if the spring is shot peened or not shot peened. If it's unpeened, then you're going to use these values, SSA and SSM. And if it is shot peened, you're going to use these values. And you're going to use these values to calculate your endurance, right? Your shear and your endurance limit in shearing. And you would use this, typically you use a Gerber, right? On the exam, I will tell you what to use. If not, then you can use Gerber. All right, and from here, once you have SSE, you can come back and then use the original modified Goodman criteria, and then you can solve for the safety factor based on that, right? So your safety factor is going to be equal to 1 divided by these guys. All right, so this is how we do that. Regarding SSU, well, we have SUT, right? We know SUT is going to be equal to A over D to the power M. In the case of a music wire, SSU is going to be equal to 0.67 SUT. And then this is the only thing that we're going to deal with. There is actually a table that you could use to link those two. In our exam, if I'm going to give you something, it's going to be a music wire, and you're going to use this SSU. Okay, this is the only SSU that you are going to need. All right. Okay. Now I would actually like to come back, and I would like to go over this lecture that I have going on here. By the way, this is what relates SUT is equal to H to the D to the power M. Depending on the wire, right? You have different types of wires. For a music wire, right? This is going to be the units in inches. This is our A. It will always be 201. And you can relate the ultimate tensile strength to the diameter of the wire, which sort of makes sense, right? Imagine, like, same material, and we know the wire will always be like a wire, right? So we can basically relate your dimension to your strengths. Now I would like to cover extension springs. And in the case of extension springs, extension spring is a spring that has a hook, and that spring is always going to be in tension. In the case of extension springs, we are going to have two stresses. One of them is going to be in the coil, which is going to be exactly like what we discussed in the case of a compression spring. And the other two stresses are going to be in the hook. So, the hook is going to come like this, right? And now, obviously it can't go straight down. You actually have to give it a curve and to begin your circle, right? So if I'm looking at this guy from the side, right? If I'm looking at this guy from this direction, I'm going to basically see this, right? And I'm going to see that this guy is coming like that, and now it's going to make another radius to actually blend in with the coil, right? In that case, we are going to have two stresses. One stress is going to be at A right here, and then that stress is going to be equal to two things, right? It's going to be equal, one portion of it is going to be the axial, right? Which is your force divided by pi d squared over 4, right? This is, considering this element right here, right? So in this element, what do we have? We have tension caused by that force, which is this component, and then we have a bending moment, right? Which is Fd divided by pi I, right, in this case. So we are going to use Ka, which is a factor that takes into account the fact that you have also, a spiral curvature in that spring. So in the case of an extension spring, we have, this is our first point, right, which is sigma A. It has bending stress, right, as a result of this force, and it also has an axial stress, right, because that element is not below the force directly. We have a moment, and Ka is going to be this. C1 is going to be 2R1 divided by D, where R1 is actually the radius of the hook. The other stress that you are going to have is, if I'm looking at this guy from this side, I'm going to actually have another radius here, right? And you guys, like I said, you're going to be able to see this if you look at this guy from this side, right? Looking at this guy from this side, you will see that you are going to have this R2. And here, somewhere along here, we are going to have a shear stress, and then this stress at this element right here, B, which is right here, right? This is the second element. Here we are going to have this guy, which is the shear stress that we calculated earlier, right? And in addition, it has a basically that is going to be this guy, just simply KB, right? And KB is you're gonna be using this radius R2 in this case. All right, R2 is different from R1, so make sure you are getting that. Okay. Now let me just get rid of this so I can. Okay. Just 1 second. Sorry about that. Okay. So these are, different types of extension springs. Like I said, extension springs, they have a point here, which is going to be under axial stress, right, as a result of axial force and bending moment. And somewhere along here, in the case of this guy, right, looking at it from top, this point right there at the bottom of the hook is going to be subject to pure shear, right? And in this case, this is R2, right? R1 is going to be here. R1 is going to be, I'm sorry, the radius of the hook, right? So let me just draw that quickly. So this would always be your R1, right? And then R2 is going to be this guy. All right, and we need those two to be able to calculate the stresses in the hook. And just like in the case of any mechanical component, you have to calculate the stresses at the areas that you think are going to have the highest stresses, and the highest one basically is going to dictate your maximum force, right? Or is going to give you the lowest safety factor. And the weakest element is going to be your control element in your case. Okay, in the case of the overall tension spring, what we have is we know the extension spring will always going to be in preload, right? So if you try to pull on it and then let go, you see that spring will always come back to this position or this direction or this initial orientation. And basically, as you are to create deflection, you have to create, or you have to apply a force that is greater than the preload in that extension spring, right? So that is why we see the KX diagram of that spring, or the stiffness of that spring would look like this, right? You apply a force, if your force is below Fi, you're not going to have any deflection, right? So as long as my force is below Fi, my deflection is going to be 0. Then if I increase my force more than Fi, now my deflection is going to start to build up. Okay, so the force in the spring is equal to Fi plus Ky, where Y is the deflection of the spring. The free length of an extension spring is going to be equal to this equation, and the reason why it is actually equal to this equation is L0 is going to be equal to D. D is the wire diameter multiplied by the number of body coils, right? So 1, 2, 3, 4, etc. Count these, multiply them by the diameter. You're going to get this length of the body, which is D times NB. Plus, you actually have the hooks, right? And 2C, C here is a spring constant. We remember that I'm gonna write here. C was equal to large G over small d, right? So 2C is going to be equal to 2D divided by D, right? So L0 is going to be equal to D multiplied by 2D over D minus 1 plus mb, and this is going to be equal to 2 times the diameter, right? This diameter, which makes sense, right? So we have one diameter over here, hook diameter, and then another diameter of the hook, plus we have d multiplied by number of body coil minus 1. Essentially, we are losing one coil in this equation as a result of adding these two together over here. All right, so just remember that. So the free length of an extension spring is going to be equal to 2 times d. Or actually, I think the reason why we lose this is because the reason why we lose one body coil is because we have a mean coil diameter here, right? So the length of the hook is from the inside of the hook. So inside of the hook, you're losing half a diameter on either side. That is, adding them up, you're losing one diameter in total. All right, so number of active coils in the case of an extension spring is going to be equal to NA equal to number of body coils plus G over E. And the reason why we have this G over E on this end is because we are adding the fact that we are essentially treating these hooks as number of body coils, right? So G over E will take into account the deflection that would occur as a result of this force being applied on that spring.